Okay, Assalamualaikum. We meet again for the second part for the tensile test. Okay, for this second part, I will explain about the properties obtained from the tensile test. Okay, I think in my first part of videos, okay, I already explained in stress strain curve, you have the elastic region, you have the plastic region, and then you have the, I would say, the fracture region, or you can say as well the elastic stage, the plastic stage, as well the fracture stage. Okay, for elastic, if the metal when you perform the tensile test, okay, and then the sample uh, doesn't exceed the U strength point or U strength value, and then let's say if you pull the sample and then doesn't exceed the U strength, and then you release the clamp, and then that metal tend to go back to original shape of its dimension. Okay, so how about the atom arrangement in the metals? Okay, when uh, you do the tensile test, okay, you can see at the first stage, at the initial, this how I say, the atom layer, okay, uh, arranged like this, and then when you apply the small load into the opposite direction, or even in the one direction, but at the upper part you fix the metal rod, and then you pull, and then you can see when the metal is stretched, the atom is arranged like this. Okay, there's something like uh, gap between the atoms layer, and then when you release back the force or the clamp, they tend to go back to the original shape, and then it's arranged, the atom arranged back into the original position. Okay, I give you a really simple example how to analogy what is the elastic means. Okay, I think all of you know about the rubber band, right? What happened if you pull the rubber band and then you release the force? Okay, this rubber band tend to go back to its original shape. Okay, if we plot this kind of phenomena into the stress strain curve, okay, this one I can say force versus strain. Actually, this one the stress strain curve. Okay, when you say that material is that metal is elastic, okay, you should get this kind of linear graph. But if you get this kind of something like how I say, wavy shape, okay, you can say this one is a non-linear elastic graph. Okay, what we can get from the elastic region? Okay, number one, I think you understand about the Hook law or Poisson ratio. I think in one ABB 113 you have learned this, so I no need to explain more on this. Okay, normally the Hook law is very famous equation. We want to explain the elasticity of the material or metal. Okay, normally when we plot the stress of a strain, the slope of the graph normally we call as a modulus of elasticity, or we call as a Young modulus. Okay, that's really important. Let's say uh, let's say you have two material, the E value for material A is, let's say, 1.0, material B is about, the modulus Young is about 2.0. So meaning that in this case, more higher the modulus Young value, meaning that the metal is more elastic. Okay, but of course more higher the modulus Young, more stiffness the metal or the material. Okay, number two is the Poisson ratio. Okay, what's the Poisson ratio? Normally the strain in the x direction versus strain at the y direction. Normally the Poisson ratio exists inside the metal itself. Okay, just now I give you example for the elastic. Now I show you the diagram. Okay, how this plastic deformation happen in the metal. Okay, Tadi saya explain in elastic, the atom layer arrangement can be positioned back themselves into the original shape and place. But if the material is a plastic metal, meaning that exceed the yield strength point, so meaning that the material, the arrangement of the atom is might different. Okay, as you can see, when you apply the small load on the plastic metal, okay, the atom tend to shear. Okay, when you stretch it, the atom arrangement tend to uh, shear. And then when you release the load, okay, when you release the load, you cannot this atom cannot rearrange back into its original position. They tend to remain as it is. Okay, again, in order to give you simple analogy, I give you plasticine. Okay, I think I already mentioned before, when you convert into the this f over strain value, so you can get the something like non-linear graph, meaning that that's one is the plastic metal. Okay, I don't want to talk about this because I already explained this in the first video. Okay, normally for plastic deformation we call it as a permanent, because when you pull, you release the load, or you open the clamp from the machine, so that metal cannot go back to its original position. Okay, again, this one, what happened, okay, when we talk about the phenomena. Okay, I think I already explained in the first video, when the sample in the first stage or elastic region. Okay, the dimension of the sample, even the area of the dumbbell shape, as well the length of the dumbbell shape, still remain as it is if you remove the load. However, when it's reach its yield strength point here, okay, not yield, this one not yield point, okay, this one we can say is the ultimate tensile. Okay, because as you can see, if this one is the strain hardening, you can get straight and then something like little bit curve here. Okay, but this one, they go straight and then drop. Okay, meaning that they go for plastic region, and then suddenly no, I would say strength hardening condition just reach its ultimate tensile strength, and then the necking formation start to happen. Okay, but this case, okay, you can see here, in this case, when the sample is increased, okay, this necking will start and then elongate back. Okay, so this graph is not so important, because this one just to portray how you interpret the results. Okay, just now is a permanent deformation, is a slip motion of the location, capable of, this one you can read. Okay, no problem, because I already explained in the previous. Okay, I think this one I will explain about the offset. Okay, let's say you doesn't know the yield strength value for that particular material that you use. Okay, what you can do is that you can straightly do the test using the UTM machine. Okay, UTM machine, universal testing machine, and then you select the tensile mode, and then you performing the test, and then you get this graph, and then you can calculate where actually the use strength value for for this metal. You can use the 0.02% or 0.2% from the offset from the strain. Okay, so it's really important. Okay, what happened at the yield strength? Okay, uh, in simple word, okay, in simple word is very easy like this. Okay, I give you simple analogy. How to say? Okay, something like you want to climb the Mount Everest. Okay, the Everest is the highest mountain in the world. The highest mountain in the world. Okay, imagine the peak of the Everest mountain is the maximum yield strength value for metal. Okay, imagine that, I give you simple analogy. Okay, just imagine the peak of the Everest mountain is the yield strength value for the metal. Okay, let's say you climb the Everest, and then you feel that. you exhausted to climb, and then when you're exhausted, definitely you will return back to the base camp, to the base camp. Okay, so meaning that you are still elastic mode. So meaning that you want to go far but cannot reach that point, and then you go back. So meaning that you go to the original position at the base camp. However, when you climb the Everest mountain until the peak, okay, and then you success to reach the peak, okay, it's good for you because we are now top on the world. But when you stay, because in the peak of the Everest, you cannot stay for a long period because the oxygen is very thin, and then uh, maybe some of the climbers suffers from suffocated condition. So therefore, they need to go down quickly. When you go down quickly, okay, so means that you are in the fatigue condition. So meaning that you don't have any option. Okay, either you go down or you die. So meaning that from there you start to think, okay, whether okay or not, okay or not. So that's why you in the plastic deformation. That's why the graph is become slow because you go down slowly. Okay, from the mountain peak. Okay, when you convert into the stress strain curve, okay, it's easy when you talk about the elastic region, meaning that it's irreversible process, meaning that when you release the load and then the atom arrangement can be positioning back into the original position. However, contradictory, when we talk about the plastic deformation of metal, the deformation remain as it is, or we call it as a permanent deformation, and then the atom layer arrangement arranged in the shear mode, because when you pull the atom become slightly change the arrangement maybe a certain angle of degree. Okay, so yeah, in when we do the tensile test, okay, I think I touched a little bit on the previous video. Okay, when you perform the tensile test, okay, what the parameter change? Okay, imagine uh, when you pull the sample, okay, of course, the length of the sample is increased. Okay, this length, when you convert into percentage, we can say is the percentage of elongation, or we can say as a ductility performance. Okay, meaning that the higher the elongation percentage, meaning that more ductile the metal is. Meanwhile, when you calculate, okay, from this metal A and metal A is about 15%, metal B is about 3%. So meaning that metal B has a lower ductility compared with metal A. Okay, what other parameter change? Okay, you can see when you pull the sample in opposite direction using a small load or high load, so of course the cross section surface area of the metal rod or the specimen also increase, because when the necking happen, okay, of course the area as well change. Okay, in this kind of measurement, okay, we call as the area reduction in percentage. Okay, in simple word for this slide, in order to decide this metal is good, I mean this metal is ductile or not, I mean the material, the metal is, I mean contain high ductility or not. So means you need to calculate two parameters. Either you calculate the percentage of elongation as well the percentage of area reduction. Okay, maybe you can put in your note, maybe you can jot down in your notes, please put star. Okay, this one a quite famous questions, okay, for the final, even for the test. Okay, sometimes we ask you, we combine this combination, you need to calculate the percentage of elongation and the percentage of area reduction, and then you need to justify the answers by using the stress strain curve. Okay, so in this particular example, you need to understand how to translate that information into calculation as well as explanation. Okay, this one the example of the materials. Okay, so in simple word, high percentage of elongation, meaning that high ductility. Low area of reduction percentage, meaning high ductility. Is it? You get it? Okay. High percentage of elongation, meaning that that metal is high ductility. In contrast, when the area reduction percentage is lower, okay, that metal is a ductile metal. I hope you get this kind of information. Please jot down, okay, somewhere. This is really important information. Okay, I think that's all for my second video. Okay, I will show the next video with you. Okay, I will record and for the third part of the tensile task. Okay, so I don't plan to capture all the videos in one single recorded session. So you need to digest all the information, and then you need to think, okay, which part is important, which definition is really important. Okay, see you on my third video. Okay, bye bye.